In this video, we're going to go over the solution to problem number 1 from the 1987 AP Physics C E&M exam. So it starts off with a typical Gauss's law problem. In this case, we have a charge uniformly distributed throughout a spherical volume, so basically a uniform density sphere of charge. And we want to use Gauss's law to derive expressions for the magnitude of the electric field at points inside and outside of the sphere. So with part A, again using Gauss's law, we have our closed integral of E vector dot dA vector equals the enclosed charge over epsilon naught, and here we're using the result of Gauss's law that's obtained from the divergence theorem as opposed to looking at charge densities directly, though we're going to do that soon enough anyway. And the left-hand side of this integral, the E vector dot dA, those are always parallel, so the E factors out. So we get an E times 4 pi r squared because it's just the integral over our Gaussian surface. So we're using an imaginary Gaussian surface centered on our sphere. The enclosed charge is just the charge of the sphere, capital Q. So we get exactly what we would expect from Coulomb's law and the definition of the electric field. However, it was not allowed just to go straight to that result because they said, use Gauss's law. So now, moving on to part B, what about inside of the sphere? So we're going to consider a Gaussian surface of radius little r less than big R. And Gauss's law, of course, is still valid. In fact, the left-hand side of it is exactly what we expect. We still have the E times 4 pi r squared, but we're going to do it a little bit differently in terms of the right-hand side. We're not actually going to evaluate an integral in this solution method. My opinion is that if you can use the ratio method on a problem, then use the ratio method. It's usually going to be a lot quicker, and it's going to be a lot easier, especially on the harder problems. Now, I should mention that this would only work if the density is uniform. If the charge density rho was not uniform, then we would not be able to use this method. We would have to use an integral anyway. And I am going to show that solution method. So the ratio of the enclosed charge to the overall charge is equal to the ratio of the enclosed volume over the overall volume. So the enclosed volume is the volume of a sphere of radius little r. The overall volume is the volume of a sphere of radius big R. So that's just going to be little r over big R quantity cubed for that ratio. So now, since that means the enclosed charge is equal to the ratio of radii cubed times the overall charge, we plug that in for our enclosed charge of Gauss's law, and we've already done that in this case. So what we're left with is that the electric field magnitude inside of the sphere is K times big Q times little r over big R cubed. Now, let's pretend that the charge density was not uniform. In that case, we would need to set up the integral anyway to find the enclosed charge, where the enclosed charge in our Gaussian sphere is equal to the sum of all of the little bitty enclosed charges, the sum of all the dq's. But what is a dq? A dq, a little bitty amount of charge, is equal to whatever the charge density happens to be there times dv. That's actually the definition of charge density. It's dq over dv. Well, in this case, we had a uniform charge distribution. If it was not uniform, we would just plug in whatever our function is right here for rho of r and integrate that from the center of the sphere out toward the radius we're interested in, little r. But in this case, it is constant, so we have our charge density being the charge of the sphere divided by the volume of the sphere, which I'm actually just going to write as q over v sphere for a little while. Now this dv, this volume element, well, how much charge is in a spherical shell of radius r? Well, that's going to be equal to the thickness of the shell, dr, times the surface area of the shell. So that's going to be 4 pi little r squared times d little r, where little r is our radial coordinate. So that means the enclosed charge, well, since the density is uniform, I just factored that out of the integral. and we're going to integrate from 0 to little r. Notice I made a little change of my dummy variable here because it's kind of bad form to use the same integration variable as a boundary. So I called it r prime. Don't confuse that with a derivative r of r, but anyway. We now integrate that. Well, that's not a surprising integral. 4 pi divided by 3. Oh, that's the formula for the volume of a sphere. So this 4 pi, this r prime squared becomes an r prime cubed over 3. That's where we get the 4 pi over 3. The 4 pi over 3's cancel. And upon evaluation, we get exactly what we got in the previous situation. Again, if our sphere had not been uniform, this term would not have necessarily come out of the integral. We would have had a different term in here, and we would have had maybe a slightly harder integration, but probably not too much more difficult. But in any case, we got the same result as we expected. So then dividing both sides by 4 pi r squared, we get the result that we expect. Now, what about the electric potential? Determine the potential at the center of the sphere and at the surface. Well, at the surface of the sphere, that is easy. It's the same as the potential of a point charge. They didn't tell us how we needed to determine this, so we just recognized that, hey, this is a spherically symmetric charge distribution, so the electric potential at the edge of the sphere, which is at a distance r from the center, is k big Q over big R. Now, you did need to make sure that you identified that radius as a big R because they're asking for it at the surface of the sphere. At the surface of the sphere, little r is equal to big R. Now, what about at the center of the sphere? Here is where we need to set up an integral. Remember that delta V, the potential difference, is equal to the negative integral of E vector dot dr vector. So in this case, I'm just thinking of E vector and dr pointing straight outward, but the way that I'm going to integrate is going to be a little bit different, as you're going to see. But that's okay because of how I'm expressing my delta V. I'm saying that my delta V is equal to the potential at the center minus the potential at the surface. So in that case, we can kind of think of this negative sign as still applying, but not accumulate the negative from the dot product because of how we're defining our delta V. But in any case, in that case, we now have E of r times dr, and we're integrating from little r equals big R to 0. If we were going from 0 to big R, then we would have a negative from that dot product since we're actually going inward in this case. But anyway, I'm also going to employ the trick of flipping my integration bounds because I'm allergic to negative signs, and that's going to give me a second negative sign to cancel out this first one. So now I'm going from little r equals 0 to big R, and we have E of r dr. And now we plug in E of r dr. We move this V of r over to here because we're interested in what V of 0 is, what the potential at the center, at little r equals 0. So that's equal to the potential at the surface plus the integral from r equals 0 to big R of E of r dr. Well, we know what E of r dr is. That's what we calculated in part B. So we plug that in, and upon integration, this becomes a little r squared over 2. And plugging in those integration bounds, we get this result. Now notice that in this case, it was okay for me not to employ a change of my dummy variable little r, because in this case, my integration bound was not a little r, it was a big R, so I just kept it as is. So the potential difference between basically the potential at the center, which is really what I should have called this. I shouldn't have called this delta V. I should have called this V of 0. That's equal to 3kq over 2r. In fact, PowerPoint is so magic nowadays that it heard me on this and it automatically corrected it as I was doing this video. So that is the end of problem 1 from the 1987 AP Physics CE&M exam. Just going back through to see where the points were awarded. In part A, they awarded a point for writing out Gauss's law. And strangely, they actually awarded a point for specifically factoring out E. and then they awarded another point for plugging in that the integral of dA is 4 pi r squared. So it's possible that maybe I would not have gotten all of my points on this because I did not specifically factor e out of the integral and then show that the left side was e times the integral of dA. That's a rare thing to do. The vast majority of the time it is quite okay to go on the left side straight from here to here. But then the final point was for getting the correct answer. They wrote it as 1 over 4 pi epsilon naught times q over r squared, but we recognize that the Coulomb constant K is 1 over 4 pi epsilon naught. Moving on to part B. If we used the ratio method, then they would have given 1 point for considering a Gaussian surface, basically mentioning that you're dealing with a Gaussian surface of radius little r less than big R. I'd actually meant to write this in the solution as opposed to the part, but in any case, they also gave a point for noting that the charge density was q over 4 pi big R cubed. So that's really the equivalent of doing it like this in the ratio. And then 1 point for noting that the volume is 4/3 pi little r cubed. And then they gave a point for putting all of that together like we did down here. And then a point for the final answer. Now, if the final answer was in terms of the density rho, then you actually needed to define that density at some point, which we did in terms of this ratio. Now, in the other method, they again gave a point for mentioning that Gaussian surface, which I already mentioned, and then they actually gave 2 points for evaluating the integral, and then a point for equating in terms of Gauss's law, and then a point for the final answer in the end. Now, for part C, they gave simply 2 points for the final answer, though they took off a point if you had your r as a little r, because they specifically wanted it at the surface, which has little r equals big R. And then in part D, this part was worth 4 points. They gave 2 points for getting to a point that looked like this. And then they gave a point for evaluating the integral. And then they gave a point for the final answer. So that is how the points were distributed in number 1 of 1987 AP Physics C E&M's AP exam. So if you have any questions, please let me know.